Okay, so we know that capacitance is defined as the amount of charge over the potential difference across that capacitor. Okay, now one thing that's important is in something complex like your phone or a laptop, there might be a lot of capacitors, and depending on how you plug that into the wall, you have a certain potential, but it's not across just one capacitor. It might be across a bunch of them in a weird arrangement. And so something that we do is we look at the equivalent capacitance. So I have, a battery, and let's say it's hooked across, two capacitors that are in what we call parallel. All right. Now, this would be capacitor 1, this capacitor 2. And note, the symbol for capacitor, these two parallel lines with a gap, and I've hooked them with wires so that they're hooked to this battery, which has some potential source. Okay, and I want to know, well, what does the battery see? The battery doesn't know that there's two. The battery is just supplying a potential, or it's pumping charges based on some equivalent capacitance. So this looks like just one capacitor to the battery with some equivalent capacitance. And our question is to find out, well, what is that equivalent capacitance? How much charge would fill up on these two plates because of this potential of this battery? Okay. So the way we're going to do that is looking at this, we're going to say, okay, this is the equivalent capacitance. It's got a potential difference across it, all right? And that's the same potential difference across these ones. Okay. So we're going to say, okay, the equivalent capacitance is defined as the total charge that the battery or the voltage source is pushed divided by the potential of that source. Okay, so maybe the battery in this case. All right, now our goal is to try and see, do we know much about these? Well, one thing I do know is that the amount of charge pushed by this battery had to end up on this plate and this plate. And so if I say, well, the total is going to be Q1 plus Q2. Whatever they are, I don't know what they are individually, but I do know, sorry, Q1 plus Q2. I do know that together the sum equals the total that was pushed by the battery. Okay, so I can divide that by delta VB. All right, well, let's just take one step of algebra here, and I know that if I have a sum in the numerator and a single value in the denominator, I could separate that into two fractions, Q1 over delta VB plus Q2 over delta VB. Okay. Now the reason why I did that is because looking at this, that's awfully close to the definition of the capacitance of C1. Except I need to have the delta V of just C1. So if I look at C1, I say, well, what's the potential across C1? I think, wait a minute, I just recently learned that a conductor in electrostatic equilibrium is at the same potential. So if the potential difference across the battery is delta VB, then the potential difference across this capacitor must be delta VB, because I can connect the bottom of that plate all the way to the bottom here, which means if this is 0 here, it's 0 here. And I can connect this top all the way across here. So if this is plus 3 volts, then it's plus 3 volts right there. Okay, because there's a continuous conductor between. That means that the potential difference across C1 alone is the same thing as across the battery. So that's Q1 over delta V1. And the same argument can be held about C2. Potential difference across C2 is the same. And I could have said that faster because I already knew that the definition of capacitors in parallel is that they have the same potential, and you can connect top plates together by a piece of wire and the bottom plates together by a piece of wire. It doesn't matter if there's junctions, as long as a continuous conductor can go between them. Okay? It doesn't have to be straight. It can be all over the place, as long as I can get from one plate to the other plate without crossing over a battery or a capacitor or anything else, as long as it's just a wire. Okay, so I can then add Q2 over delta V2, and those are the definition of capacitance. In fact, that's C1 plus C2. So with that, I have now just concluded that for capacitors in parallel, The equivalent capacitance is just the sum of the individual capacitances. And that's a powerful thing we can use. Now, if there was a third one in parallel, then it would just be plus C3, and as many as you need to go. Okay, so that's one way we can analyze this. Now, another configuration, remembering in your laptop or your phone, there's all sorts of electronic components. And so, what if the capacitor, what if the battery's hooked up like this? Such that delta V battery is across the two capacitors in series. Okay, series means that I can put a dotted line box between C1 and sorry, that should be C2, apologize. Between the plate, the gap of each one, and I can create a continuous loop without crossing any other line. Okay? So another way of saying that is whatever went through C1 went through C2. Okay, that's another definition for series. Okay, now I don't like that one as good because nothing's really going through. The charge is building up here, repelling charge here, which builds up here, repelling charge here, which gets sucked into the battery. Okay, but the main idea is you can put a dotted line between their gaps and connect it without crossing anything else. All right, so in terms of potential, though, that potential is across this whole thing. So this is delta VB. So we start out the same way. C equivalent equals Q total over delta VB. And we want to find out what C equivalent is. All right, so if you think about the battery is pushing charges, and it pushed a total charge of Q total, well, how many ended up on C1? Well, all of them did. There's no other place for it to go. So all the charge that got pushed by the battery ended up on C1. Okay, well, then that means it sucked charge from C2, which left the inner plates, which must have been neutral already, have the opposite charges here. So if this is pushing, let's just pretend it's pushing positive charge. It dumps positive charge here, so this would be plus Q, and this is negative Q. Well, for these to be capacitors, that means this needs to be plus Q, and this needs to be negative Q. And that's all right because everything inside is still neutral. We have as much negative as we have positive. That's an overall neutral object, as it should have been, because there's no way of adding charge to it. There's no connecting wires. So we know that Q total equals Q1 and it equals Q2. All right, now, so we can, sorry. Yeah, they're equal. They're not summed, they're just equal. Okay, so I can't really do much with that right now, unless I do it this way. What if I go like this? I'm going to rewrite this as delta VB over Q total to the -1. That -1 means flip this. Okay, now with that inside that -1, I'm going to now write it out as, oh, hold on, sorry. I apologize, I'm not done yet. I jumped ahead of myself. Okay, let's come back. So now my question is to look at this delta VB. So delta VB is the potential across both capacitors. All right, well, what's that related to the potential across C1 and the potential across C2? Well, we learned that if I gain across the battery and I lose some here, I got to lose the rest here because I get back to where I started. And so I've got to end up with 0 overall. And so that means the potential across this one plus this one must equal the potential across this one. So in this case, I get for delta VB, that's delta V1 plus delta V2 over Q total. All raised to -1. Remember, that's an inverse fraction. Okay, now I can do my algebra. I'm going to jump this and say that's delta V1 over Q total plus a delta V2 over Q total, all to -1. But Q total is the same thing as Q1, which is the same thing as Q2. So I can write this as delta V1 over Q1 plus delta V2 over Q2, all inverted. And that is just C1 inverted plus C2 inverted. And so that's the relationship. Now we often like to write this as 1 over C equivalent equals 1 over C1 plus 1 over C2. And we often like to write it that way. So it's just kind of symmetric. We say the inverse is equal to the sum of the inverses. Okay, but this is what's really functional if we're trying to actually find that value. So the main idea is this is a good exercise. We came up with two really useful equations that we can use now. But the main idea is recognizing how charges are actually moving. The battery is a pump and it pushes charge, and those charges have to stay on wires. They're not created or destroyed. And so we saw, based on what's happening, where they would end up and how it's distributed, and therefore got these two relationships.